Welcome to college. Today we shall look at an example under mesh analysis. In this given circuit, we are being asked to determine the mesh current and the branch current. The branch current I1, I2 and I3, which are already indicated in the circuit, and also their direction are also given in the circuit above. Now, solution. First of all, we need to know the number of loops we have in any given circuit. The number of loops or meshes. In this case, we have two meshes, mesh 1 and mesh 2. So let's assign mesh current to these two loops. For mesh 1, let's assign mesh current I1, and also for loop 2, let's assign mesh current I2 as the unknown current. That is, since we have two meshes or loops, we have our mesh current to be I1 for loop 1 and I2 for loop 2. Before we proceed, let's take note that the branch current I1, I2 and I3 are dependent on the value we get from I1, I2. This simply means that we cannot determine the value of this branch current without solving for the mesh current. That is, the branch currents are dependent on these two mesh currents. For us to determine the value of I1 and I2, we need to apply KVL in these two loops. Now, the steps required to get our I1 and I2 using KVL is: step 1. Step 1, we need to assume what we call the direction of motion, that is the path we want to follow to analyze the circuit. For loop 1, let's assume a clockwise direction, and also for loop 2 or mesh 2, let's also assume a clockwise direction of motion. This simply means that, let's quickly label the circuit A, B, C, D, E and F. For loop 1, if we are moving in a clockwise direction, let's say we start from point A, we are moving in this direction, point A to B to E to F and back to point A. This is the path we want to follow to analyze the circuit. So we have A, B, E, F and back to A. Likewise for loop 2, let's say we start from point A, we move to point C, to point D, point E and back to point B. So we have it to be B, C, E, D and back to B in a clockwise manner. The next step is to assume the direction of current flow. Now please take note that we are at full liberty to assume whichever direction we want to assume, either clockwise or anti-clockwise. For loop 1, let's assume the direction of current to be clockwise, that is I1 to be clockwise. And for loop 2, let's also assume a clockwise direction, that is, for loop 1, we assume a clockwise direction of current flow, and for loop 2, we also assume a clockwise direction of mesh currents. The next step is to write out our KVL equation for loop 1 and loop 2 respectively. Let's start with loop 1. Now, for loop 1, as we agreed earlier, the direction of motion is clockwise and our loop current is also clockwise. Now let's take the elements one after the other, or the components of the circuit, starting with the EMF, the battery side, the 20-volt battery. We are moving in a If we are moving in a clockwise manner, that means we are moving from the positive terminal of the battery to the negative terminal of the battery. So we have it to be what? There is a to be plus E1, because we are moving from a point of lower potential to a point of higher potential. So we have it to be plus E1. The next element there is the resistor. The resistor R1. We are moving in a clockwise direction. So the direction of motion, this direction of motion is clockwise. The current flow I1 is also clockwise. This is the direction of mesh current, is also clockwise. So there is a fall in potential, a fall in potential. So we have it to be minus I1 R1, because the direction of motion and current are the same. From loop 1 perspective, we are still analyzing the circuit in a clockwise direction. So the next element there is resistor R3. That is, this is our direction of motion clockwise. We need to take note that resistor R3 is in between loop 1 and loop 2, is at the middle. So mesh current flow through it, mesh current I1 and another mesh current I2 flows through it, I2, but in the same clockwise direction. Now we need to analyze this component R3 from two different perspectives. From loop 1 perspective, where we have mesh current I1, so the direction of motion and the direction of current is the same. So we have a fall in potential, which we have it to be I minus I1 R3. On the other hand, minus I1 I3. Considering the other mesh current acting on it, we have the direction of motion from loop 1 perspective, because we are analyzing resistor R3 from loop 1 perspective. Now resistor R3, direction of motion is clockwise. Now the second current acting on it or flowing through it is mesh current I2. So these two are in opposite direction or direction. So we have a rise in potential, which will give us plus I2 R3. We have the last element there, which is the second EMF. We need to determine the sign of the electromotive force produced by this battery. Now we said we are moving in a clockwise motion, and please recall that the sign assigned to an EMF does not depend on the direction of current flow. It only depends on the direction of motion. So we are moving from the positive terminal of this battery to the negative terminal of this battery in this case. So we have minus E2, as opposed to this EMF E1 when we were moving from the negative to positive. In this case, positive to negative, so we have minus E2. And from KVL, the algebraic sum of all the voltage equals 0. Substituting values, we have our E1 to be 20 minus 5 I1 minus 10 I1 plus 10 I2 minus 10 equals 0. Simplifying this further, we have 10 minus 15 I1 plus 10 I2 equals 0. We can have it to be, if we take these two to the other side of the equation, we have 15 I1 minus 10 I2 equals 10. Dividing everything by 5, dividing both sides of the equation by 5, we have 3 I1 minus 2 I2 equals 2. So we can label this our equation 1. So the next step, let's write out our KVL equation for loop 2. Now, we said we are moving in a clockwise direction. So we should move in a clockwise direction. Let's take the elements or the components of the circuits one after the other. We have E2. We are moving in a clockwise direction. That we are moving from the negative terminal of the battery to the positive terminal of the battery. We have plus E2. Now taking the second element in the circuit, which is resistor R3. Resistor R3. Once again, the resistor R3, we have two currents flowing through resistor R3 because it's been positioned in between the two loops. But in this case, we are analyzing loop resistor R3 from loop 2 perspective. Now in the first case, where we have our direction of motion in the second loop to be clockwise, and also the direction of current in the second loop I2 to also be clockwise, we have a fall in potential. We have minus I2 R3. We have minus I2 R3. But in the second case, when we consider mesh current I1 and the direction of motion in loop 2 is opposite to the direction of current from in mesh 1. So we have a rise in potential, or an increase in potential. We have plus I1 R3. So we have it to be plus I1 R3. The next element in this circuit is resistor R2. The direction of motion is clockwise and the direction of current is also clockwise. So we have a fall in potential. So we have minus I2 R2 as the voltage drop across the resistor. Minus I2 R2. So the last element there is resistor R4. Considering resistor R4, we have our direction of motion to be clockwise and also our direction of current to be clockwise, that is mesh current I2. So we have, once again, we have a fall in potential, which will give us minus I2 R4. Minus I2 R4. From KVL, we have everything to be equal to 0. Algebraic sum of voltage in a closed loop equals 0.